for viewing on our website. So again, my name is Rob Rallo. Welcome to our webinar today on almost everything you know about solar modules. I'm a senior engineer with Sunwise, and I have got over 25 years of experience in the off-grid business. I've been doing this since around 1990, 1989. As we do have a lot of material to cover, again, we're trying to cover almost everything you know about solar modules, so to try to do this in an hour's time. We are going to try to go quickly. If there's something that we missed, you're always welcome, or something you didn't quite catch, you're always welcome again to go back and review the webinar online. As always, please ask questions in the question box, and I'm hoping we have time at the end to get to some of those. I'm just going to briefly skim through Sunwise a little bit. Again, company's got over 20 years in off-grid business. We do standalone hybrid systems, battery backup systems. We have engineering and manufacturing facilities and sales offices across the country. We also do services like technical writing, troubleshooting, training, engineering, design, support, and things like that. Okay, so let's get started with today's agenda. We're going to cover a lot of material today. We're going to start with the types of solar modules. We're going to go into array terminology a little bit, because that'll help when we start talking about the different parts of the module. It's helpful to understand how that's defined. Talk a little bit about array sighting, orientation, and tilt angle. We talk about shading effects of solar modules. We talk about testing of the modules and the array. We may not cover that in depth. We may not have time for that. We'll see. And what we do not cover on this webinar, we will cover in more detail on our next webinar coming up on 3 weeks from today. It's going to be August 23rd. August 23rd, same time as usual. We'll be covering that. So if you haven't signed up for that one already, please feel free to go ahead and sign up and register for that webinar as well. We're going to go in depth on system troubleshooting, and again, we'll cover whatever we don't cover today with regards to the module testing and troubleshooting. And then if we have time as well, we'll go briefly into a little bit into commodity box requirements. Okay, so let's briefly talk about types of solar modules. Solar modules are kind of broken up in a couple of different sizes. We have the small format, which is more of your off-grid ones. These are ones that are usually they can be integrated into products. They might be custom made. We've also got thin film, which can be bent. Thin film is a amorphous crystalline type of thing as opposed to crystalline. The idea behind the amorphous is it can be made flexible. If you use a lot of backpackers like those, because they can roll up and stick in their backpacks, the negative of those are that they are about half the efficiency of a regular solar module, so you need twice as much area, and sometimes that can be a problem. So a lot of people generally go for the crystalline unless there's a specific need the thin film and the amorphous. Okay, most of the 12-volt modules nominal for battery charging will be of a 36 cell size, and I'm going to try to get in a little bit more in that later, why they are 36 cells. We'll briefly talk about that. Also, I think we've covered that pretty well in some of our other webinars with regards to temperature effects on solar modules. It goes into that as well, why it's 36 cells, but we'll touch on that again briefly here. The 60 cell modules are generally used for grid tie applications. They can be used in off-grid, but they must be used in the maximum power point tracker. Some people think they're 24-volt modules. They are not. They're more like a 20-volt module. So if you put several of them in series, then you can get enough voltage with MPPT to charge a 24-volt or a 48-volt battery. But again, they have to use with a maximum power point tracker. And the 72-cell modules, which get rather large, are great for using for large 24-volt and 48-volt systems. And again, they can get rather large. You can find them in the smaller sizes. They do come in. Sunwise does sell them as small, I think, as 20, might even be 40 watts or 20 watts. The more common ones are as big as 320 watts or so. Great, again, great for working on large projects. They're very cost-effective for that. And as a matter of fact, they're as cost-effective as the 60-cell modules, and making me wonder why people even bother with the 60-cell modules for off-grid applications when you can use the 72-cell modules instead, because they're just as competitive price-wise. Okay, along with the different types of modules, they have a couple different connection options. Most of your Class 1 Div 2 modules, and let me talk briefly about that as well. Class 1 Div 2 hazardous rating modules, they're going to have a junction box on the back of them. A lot of your smaller ones will as well. Those junction boxes allow you to connect with a cable and or conduit. Okay, you're going to make actual terminations either with ring terminals or with an actual box lug inside the junction box. Okay, so it's going to be an actual screw terminal in there for you to connect to. The MC4 and the Amphenol H4 are essentially the same thing. They're just a quick connect type of mechanism. As a matter of fact, some people even interchange the H4 with the MC4, but it's just a quick connect cable type of connection system where they literally just click together and they require a special tool to separate them. That's very common on the large format modules. And then there are other ones as well. The one that I always think of as other is just a pigtail on the really small modules, like the 5, 10 to 20 watts. Sometimes just for cost-effective reasons, they literally just have like a 15-foot piece of wire coming out. I think it's generally a tray cable, just a 2-connector tray cable with a red and black wire inside. So you might find that as well on some of the smaller modules. Okay, I briefly mentioned monocrystalline and polycrystalline. In terms of performance, they're very similar. The monocrystalline is more efficient, okay? It's going to have a slightly better conversion ratio from the amount of sunlight to the amount of power out. The problem with them is that the monocrystalline, because of the way they are produced, are in a round mechanism. So it's literally, it's actually grown in a cylinder. That's how it's done, and they basically cut it in little wafers. So because of that, they're always round. Now, you don't see them round in solar modules anymore. What they do is they actually clip it off to make it somewhat square, but they're never 100% square because that's cutting off too much of the cells, making it expensive. So if you ever see a solar module that has kind of a diamond pattern in it, that's typically going to be a monocrystalline. And what they've done is they've kind of left the rounded portion of the corners. When you look at the rounded corners, it kind of looks like when all the cells get together, it looks like there's a little diamond pattern in there. So that's typically, I can tell a mono from a poly. Now, because of that, there's still that little area in the solar module that's not being used because they're not making a perfect square with the monocrystalline. They're kind of leaving those rounded corners, that little diamond pattern. So what ends up happening is that when you look at the overall module efficiency, the difference between a mono and a poly is almost none. You might find the mono is slightly more efficient, but the difference is very minimal. And because of the way that the monocrystalline is made, it's generally a little bit more expensive. So you'll find that a lot of the modules end up being polycrystalline instead, just because to produce it is a lot easier and cheaper to do than the mono. And again, once you go ahead and kind of slice it and dice it and put it in a solar module, the actual module efficiency is very close to the same. The increased efficiency is very minimal. Okay, there are various certifications you can have for them. Most people, of course, should be familiar with the UL 1703. That's commonly used for solar modules specifically because it's being used for residential applications. There's also international standards like IEC 61215, and I mentioned earlier about the hazardous rating, the Class 1 Division 2 hazardous rating. That's important for some oil and gas applications. There are other ones as well, ISO, which could be used for quality, CE, ITL, IEC, CSA, and a whole bunch of other ones as well. Again, the most common ones you're going to probably find here in the US are either the UL, IEC, or the Class 1 Div 2 hazardous rating. Okay, let's talk about array terminology a little bit. This is just a quick diagram, and this is all going to be coming from the National Electric Code. I took this strictly out of the NEC because that is kind of the standard for this. You'll see from the diagram here that you've got blocking diodes, string fuses, solar cells, the module, the panel, and the array. I'm not going to really talk about blocking diodes too much because they're really not used anymore. Blocking diodes are kind of an old thing. Those have mostly been integrated into the charge controller, so you don't really need to think about them or worry about them much anymore. But what isn't shown here, we will talk about, is bypass diodes. Those are important, especially for troubleshooting, so we'll touch on those in just a minute. String fuse is also very important, and I will talk about that more when it comes to when a combiner box is needed, so keep that in mind. Do you need a string fuse for each string or not? So again, that'll come up when you need a combiner box. So let me go ahead and define some of these other things a little bit further. So let's talk about briefly what is a solar cell. And the solar cell is kind of the smallest device that generates electricity when exposed to sunlight. And so basically, it's really, if you look at the symbol in the lower right corner here, that's a symbol for a solar cell. If you notice, it looks like a diode. And if you look at it again, it's kind of almost the inverse of a light emitting diode, an LED, and that's essentially what a solar cell is. It pretty much is the exact opposite of an LED. With an LED, you put current through it, you get light out. With a solar cell, you put light on it and you get current out. It's pretty much as simple as it is. So again, which basically just means it's basically just two dissimilar types of semiconductors that allow current to flow through it. It's what they call an N and a P layer. So the top layer is an N, the lower layer is a P layer. You've got this layer in between, which is the junction of it. And then they put metal contacts on the top for the electrons to flow through. And then there's one on the bottom too that's solid that allows it to return. So as the sun hits a solar cell, the photons from it excite the electrons inside. The electrons then group to either end. They collect on the electrical conductor here, which is basically a metal strip. And then it goes out, flows through your load or battery, whatever it is, and it comes back to the other side, and that creates your loop. Now, each cell, it's saying here it's about 0.58 volts. That's pretty much open circuit voltage, VOC. The maximum power point voltage is more like about a half a volt. So 0.5 is usually what we end up using when we talk about discussions with this. Okay, so that's the smallest unit. Now, you're going to string together the solar cells into a solar module. And again, as we talked about before, the most common ones are 36 cell for a 12-volt module, 60 cell for grid tie applications, and then 72 cell modules, which are all strung, all the cells are strung in series to get you the 24 volts. Okay, so a module is defined as a complete environmentally protected unit consisting of solar cells, optics, that's kind of the glass, and other components. They also have so that the glass itself can be used to help make certain it captures as much sunlight as possible. Okay, so then the solar modules are put together in a collection that we refer to as a panel. So again, a panel is a collection of modules mechanically fastened together, wired and designed for field installation. Okay, then the array is a bunch of panels assembled. Okay, so it's a mechanical integrated assembly of modules, panels, with a structure and a foundation. You may have trackers or other components as well. You don't really see a lot of active tracking anymore, primarily because the cost of the active trackers is more than just adding additional modules for the performance you get out of it. So with the modules being so inexpensive nowadays, it ends up being more cost effective just to add additional modules than it is to go to a tracking system. There's also maintenance required with tracking systems, and they are more prone to failures. So in the end, it ends up being more cost effective just to add additional modules than it is to go to a tracker mechanism. Okay, now just going to talk about the bypass diode as well here briefly. What a bypass diode does is it protects against a hotspot that is caused when the module is partially shaded. Not completely shaded, but partially shaded. We're going to talk about more about shading as well later on in this webinar. Okay, but you will notice here that the diode, again, there's a blocking diode we talked about earlier, and again, they're really not used too much anymore. This is pretty much integrated into the charge controllers nowadays. But the bypass diode, you'll notice that the line on it, the blocking end of it, is up here at the plus. So what happens is the current's pretty much flowing out of the module, through the battery, and back this way through the array. Now, so any current coming this way is blocked. But if the cell is shaded, it will allow this blocking diode to open up, allowing this module to be bypassed. So the current can still throw through this one, but not this one if there is a shaded cell. We've actually recently just done a tech note on this as well. That's up on our website talking about this. But what ends up happening is that, as I mentioned earlier, a solar cell is like an LED, except when you put sunlight on it, it produces current instead of needing current. Well, when you take the sunlight away, it actually ends up taking current. So it will start to consume energy or power, which you do not want. The blocking diode prevents then the battery from the current from the battery flowing back to the panel again. So at nighttime, we don't talk about this much anymore because all the charge controllers stopped this. But in the old days, we used to have to put in blocking diodes because literally the battery could discharge through your solar array at night. Okay, so again, that stops it from nighttime, but when you have a partially shaded solar module, if you shade a cell or two, those cells could still consume the energy. Okay, now the charge controller prevents it from coming from the battery, but it could come internally. So when that happens, that can create a hot spot. All of a sudden, the energy from all the other cells can dump into that one cell that's being shaded, and it can literally cause damage to the module. If you look at the back of a module and you see kind of a burnt mark on it, that's probably a hot spot caused by a bypass diode not functioning correctly. So they are very important still. They are generally already in a solar module, and we'll show that more when we get into troubleshooting. You'll see a junction box with those in there, and we'll talk about those in more detail then. But it's very important to understand those when it comes to the solar module, what it's doing, how it works, and how that can affect the performance of the solar array if one has failed for some reason. Okay, so now let's move on to sighting. And we're going to talk about shading more in detail, as I said before, but in general, try to avoid it at all costs. It is a very serious problem. Even shading one cell can be a big problem. We're going to talk about that in a little bit. So again, it's best to avoid it completely if possible. Again, that includes hillsides and cuts if it's in a valley or something like that. Obviously trees, poles, that's another one. A lot of times you might be having an antenna or other devices that are nearby that are not already on the pole with the solar module that may actually block it. So you need to be very careful of that. You also need to check for shading conditions in the summer and the winter, as they can be different. A good example of that is especially with vegetation that can grow up in the summertime. Everybody's always worried about the winter, but the summertime is actually a bigger problem sometimes when it comes to vegetation from trees and other things that may grow up in front of the solar array. And again, I'll talk about that more when we talk about shading. So again, best to try to avoid all that stuff if possible. Okay, orientation. In general, the solar array should face south in the northern hemisphere and north in the southern hemisphere. When you get within about 10 degrees of the equator, there are a few times when there's exceptions to that rule. That's why I say generally, but right around the equator, because of the rainy season, sometimes you may actually flip that. But that's on kind of a case-by-case basis if you're around like the Panama area, Colombia, something like that. So I think for Northern America, you don't have to worry about that too much. Plus or minus 10 degrees from true south doesn't really matter too much. It's insignificant. It's just a few percentages of loss. That's not much at all. But if you start getting around 20, 30%, it could be a very serious problem, especially if you start getting the 40 degrees more off from true south. You're going to find that it's going to impact the performance of the solar array, especially in the wintertime when you might find your system failing. So it's very important to try to get within 10 degrees of that true south. And with regards to that, it is best to use GPS for that if possible. They're the most accurate because they're electronic. If you're using a compass, then make certain you compensate for magnetic declination. Basically what that means is, here's a map of the United States for a declination map. What it means is that magnetic south isn't true south. That there's a slight deviation that constantly is adjusting, by the way. I can adjust by about a half a degree per year, actually. So these maps are constantly updated. This one's actually from 2010. It's probably already outdated by about 3 or 4 degrees already because of that shift. The black line in the middle going right through pretty much about New Orleans there, on up through Minnesota, that is 0. So at that point, there is no declination. That is where true south and magnetic south are the same. But as you deviate from that, especially you can see as you get into Southern California, you can be off by as much as, because there's 10 degrees right there, so that's 12, 14, 16 degrees here. Sorry, there's 15. 13 degrees right in this little area. So if you're in the southwest and you're facing your module, what you think is magnetic south, you're not. You're already off by 13 degrees right there. Same thing is true when you go to the east. Again, you'll see this is the minus. So over here, like in the Carolinas, you're off by 10 degrees right there. So again, just keep that in mind when you are sighting your solar system to make certain to compensate for that. Or just use an electronic compass, basically a GPS, and you don't have to think about it. Okay, and I just want to kind of show this as an example of these are two different solar modules and two different poles. Excuse me, that were at a site location that I was at recently. And the first thing I noticed was if you take a quick glance, you got two things going on here. One, you've got solar modules are not in the same plane, so somebody's not facing south correctly. So that tells you that, again, these are two completely different installations on the same site, so somebody got it right and somebody different. But if you see something like that, that's a quick indication of somebody's not right. You might want to pull out your compass and double check who's wrong. The other thing is you'll notice that the solar module in the background there, it's being shaded by the pole from the solar module in the front. And even though you might be thinking, oh, it's just a little line, it's not a big deal, it is. It actually takes out the entire solar module so that it no longer functions. And we will talk about that more when we talk about shading in a minute. Okay, so that's orientation. Tilt angle. Tilt angle is also pretty important with regards to same thing as facing south. The tilt angle is set to maximize the insolation the worst month. So generally, it's going to be for winter. So generally, you're going to put the tilt, you're going to put the array at an angle to maximize the output of the solar array in the wintertime. So for most of America, this is going to be North America. It's going to be slight latitude plus 15 degrees, excuse me, or somewhere between 45 degrees and 65 degrees for most of the U.S. If you're in the south, about 45 degrees. If you're going to be up more north, Boston, Seattle area, going to probably be closer to 65. And again, just like with regards to the orientation of true south, if you're off by a few degrees, it's not going to matter that much. Plus or minus 5 degrees is not a big deal. If you're still looking at 10 degrees or more, then it could be a problem. The other thing to note is again, this is for maximizing the output in the month with the lowest solar insolation. If you're going to be doing this is very different than maximizing the annual energy contribution output. Okay, so if you're doing a grid tie or a hybrid system, you are going to go to a lower tilt angle to try to maximize the energy throughout the year because you're not worried about the worst month. You're trying to get the most out of the solar array. Okay, but in an off-grid system, we don't have the luxury of having additional sources of energy. Any standalone system, additional sources of energy to charge the battery with. So you want to try to get the maximum in the worst month. So that's why you always adjust your tilt angle for that. Okay, let's get into shading effects now. Okay, and this only applies to multi-crystalline and single crystal modules. It does not apply to thin film. Thin film modules are a little bit different, but we don't really work with those too much. Like I said before, most modules nowadays are all either multi or single crystalline. And again, this applies to all of the crystalline solar modules. And the thing is that it is going to be a bigger effect the more modules and cells you have in series. I'm going to show why. And I mentioned earlier about how the solar cell produces approximately half a volt. So a 36 cell module will produce approximately 18 volts of peak power. And that's because they're all wired in series. So again, when you wire them in series, the voltages add. So, 36 times half a volt gives you the 18. And you put solar modules in parallel to increase the current. Same thing's true with batteries. So, wiring modules in the series increases the voltage, and then again, wiring in parallel increases the current. The output voltage varies little with the sunlight conditions, but the output current is very linear, is directly linear to the amount of sunlight that hits that module. So what ends up happening is that as the, so just like because they're all in series, it's a weakest link issue. So whichever solar cell is putting out the least amount of current, that's how much current is coming out of the entire module. And if you've got additional modules wired in series, then that means the entire string is now limited to the weakest cell. Okay, very important to understand that. And I'm going to show you a little. A diagram on that in just a minute to try to emphasize that point. Okay. Let's see. So to try to summarize it, let's say you have a solar module that produces 8 amps under STC standard test conditions. It's going to, and let's say, so that's based upon, STC is based upon a radiance of 1,000 watts per meter squared. Let's say we have a sunlight conditions that are only about half of that, about 500 watts per meter squared that day. That means the solar array is only going to produce 4 amps. And again, that's very linear. So the amount of sunlight that directly hits that solar cell, that solar module and array, is exactly how much you're going to get out of it. Okay, very linear there. And the voltage remains fairly consistent unless you start looking at temperature effects, and we've got a whole other tech note on that. Okay, I already mentioned the weakest link. Okay, so if you shade, so basically what ends up happening is if you shade a single cell, the entire module output goes to 0. So if you go back to that photo I showed earlier, that pole was shading more than one cell, but basically that pole causes that entire solar array to go to 0. So I think a lot of people don't realize that, especially when it comes to shading from trees or other vegetation. Again, only shading a small portion of the solar module is enough to make the energy out of it, the current out of it, go to 0, which can be a very big problem if you only have a few solar modules in a system. So to kind of emphasize that point, these are examples of where shading, a partial shading, will drop the current by half. So if you shade just a corner of the cell or this little bit down here or this little edge of the solar array, the entire solar module output now is going to be half because of that. And worse, all I have to do again is shade one cell, and the entire output now from this goes to 0. So again, keeping in mind all these cells here are all wired in series. So if you take this out, all the current now is 0. Okay, so very important to keep that in mind. And this is just an example of a photo I was helping somebody troubleshoot recently. They didn't realize it, but again, some of the corn had grown up enough that it was starting to shade the solar array. And again, you only need a leaf or two covering one cell, and all of a sudden the output goes to 0. Okay, and actually there's a battery box here you almost can't see because of the corn. So, and this could be true, and it's kind of funny. I've actually done some troubleshooting calls where all of a sudden people have trouble 2 or 3 years later, because what had happened was when they went to install the system, they cleared out all the vegetation, and then a couple of years later, as it grew up, the vegetation grew to start shading the solar array again. So just keep that in mind. We'll talk about that more in troubleshooting, system troubleshooting. When you go out to site sometimes, just this is also important with maintenance, just do a quick inspection on stuff. If you see vegetation that has grown up that can be a problem, you need to trim it back or cut it down or whatever it is to make certain it is not shading the solar array, even just a cell. And that's why I get back to, again, you don't want any shading whatsoever, because just shading a single cell can render that module or even that entire string output to 0. And if you've only got, like in this system, if you've only got 1 or 2 solar modules, charging that battery, having that go to 0 means that battery's not going to get charged and you start having failures, which you really do not want. So just keep that in mind that even a small amount of shading can be a very big problem. Okay, now keeping all of that in mind, we're going to get into now basic PV module testing. And there are 2 tests that you can do that are that are quick ways to figure out if your module is performing correctly or not, and whether it's a problem or not. Okay, and we have one of them referred to as the VOC, or open circuit voltage test, and the other is the short circuit current test, the ISC test. We're going to focus right now just on the VOC test because 75 to 80% of what you need to know you can learn from that, but there are some things you can learn from the ISC test, and we're going to go ahead and table some of that for our next webinar with regards to system troubleshooting. Okay, so now depending on the reason for testing, the VOC test can be done at either the controller, the combiner box if one is present, or at the solar module. It can also be done on the strings if you have 2 or more modules wired in series. You can be done on the string test as well. Okay. It needs to be performed with the module isolated or the panel or array isolated from the rest of the system, and it's best to be done in full sunlight conditions. again, it's important to have it disconnected, because if it's not, then you're not reading the open circuit voltage of the solar array. You're actually, if it's still connected to the system, you're reading whatever's going on with the battery, the charge control, or everything else. And those readings may give you false information on the solar module. Now, those readings can be important for troubleshooting purposes otherwise, and we'll talk about that in our next webinar for system troubleshooting. But with regards to whether the solar array is performing correctly, you want it isolated so that you can confirm that it's the solar array and not something else that's the issue. So, for that being said, having an easy way to disconnect the array or module for maintenance purposes and troubleshooting purposes can be very advantageous. So having a circuit breaker in there or some type of switch is a lot easier than having to disconnect wires or having to try to remove a fuse. So, a little plug for Sunwise there. For our systems, we always use circuit breakers on the array side. It makes it much more easier to do this than some of our competition that does just use fuses or none at all. Again, disconnecting wires in the field is not fun. We talk about the short circuit current test. The other thing about it is those wires are live. So when you disconnect it, when you have this in your hand, you have to always keep in mind that now there's a shorting hazard as well. So again, trying to have a disconnect in there like a circuit breaker or a switch of some form, really nice to have from a maintenance or troubleshooting perspective. Okay, you need to have a multimeter for this. One, of course, is capable of reading DC voltages. And if you're going to do a short circuit current test, it has to be able to read the DC current as well. And you're going to want to inline for that one, for the current. Additionally, you're going to want the manufacturer's data sheet. Generally, they can also be found on the back of the module. Most solar modules have that information, the rating of the module on the back of it. The problem is years go on, unfortunately, that stuff can get faded in the sunlight. So if you're working on an older system, that information may be faded, and you might be just looking at a blank label on the back, unfortunately. So having the manufacturer's data sheet can be handy. So just kind of a sample of a data sheet. And again, we're going to be looking at the open circuit voltage or short circuit current, these numbers over there. We're going to be looking at. Okay, so again, you're going to look at those. The other thing is you can also see there's also, going back here, is also NOCT ratings. We're going to, either one, because we're just kind of looking at ballpark values. One of the things to keep in mind is that if you're within about 10 or 20% of the rating, you're probably close enough to understand what's going on. Solar modules themselves will derate over time about somewhere between 0.5% and 1% per year, so there is a natural degradation on the output of a solar module. However, that is a very slow degradation. And we're looking at just kind of basic troubleshooting at this point. We're not actually confirming whether the module meets its actual factory rating anymore. We're just trying to figure out whether it's functioning or not. So we're just going to kind of look at the basic numbers again. So for discussion purposes, NOCT or ISC values are acceptable to use. Okay. So to perform the VOC test, you're going to simply, with the, and this again, it's going to be done at either the controller, the commodder box, or the module itself, any of those places, disconnected from the rest of the system. You're going to simply put your multimeter, positive lead on the positive wire and the negative lead on the negative wire. And just showing a couple of different pictures and diagrams here. This is a junction box one with an output cable. You could do it there, or you could do it inside the junction box as well. Here at the controller, again, you could do it here. Again, although this probably isn't as accurate unless the battery's been disconnected, because again, it's going to throw it off. So I would actually recommend actually taking it at the circuit. You can take the negative from there, but I would actually take it at the circuit breaker with the circuit breaker disconnected. I would take it at that point. That probably be a more accurate way to do it. The neat thing here is that, as I mentioned, going back to here, you're going to put your plus and the plus and the minus and the minus. If you find out you're getting a negative value, then that's going to tell you that you've reverse polarityed it. So one of some of the things you can find by testing those wires here is you can look for reverse polarity. You can see if you got a short or an open circuit, and you can see if you've incorrectly wired the array. In other words, you may have made an incorrect wiring in a junction box, or you may have, if you've got multiple modules being used, you may have done your series parallel connections incorrectly. So these are things that you can find by testing at the controller. By testing at the combiner box, you can find pretty much the same information. Reverse polarity, that's a big one I see a lot, by the way, when I get a lot of troubleshooting calls. People reverse polarity of the wires, especially when you're working with the multi-contact connectors. It's very easy to have those wires get confused, and when you're terminating them, either in a combiner box or the charge controller, because everything's all black, it's easy to get confused. A lot of times people ask me how I know if the plus or the minus. I say the simplest way to do it is just take out your multimeter, put it on the wires, and figure it out that way. That way you're never wrong. And once you do that, if you want to label that wire with some type of tag or red electrical tape or something so that you know, that's not a bad idea either. But the best way to confirm, again, is just use your multimeter. And again, you're looking for open circuits, short circuits, or incorrect wiring. Okay, if you're at the PV module, again, you can find incorrect or loose wiring, bypass diodes. I'll get into that in some more detail in a minute, but a failed bypass diode or a failed module for that matter too. I've seen loose wires either on this side of the terminal block, or I've seen on this side coming off the back of the module. This one is actually showing solder ribbon cables, so I doubt that's going to be an issue in this case, but I have seen it where they actually have wires that come out that go into, that get connected to a screw here, and you got a loose connection. I've seen loose connections from the wires coming in from the output wires. Especially over time, I've had, again, calls from systems that I've installed for 5 years, all of a sudden are giving people trouble. And what's happened is that through thermal cycling, what ends up happening is that over time, as you go between night and day, you can have temperature swings of somewhere between 20 degrees and 30 degrees, depending upon where you are in the country. And it's even worse in the back of a solar module, because solar modules get really hot. They can actually go there's a delta sometimes as much as 40 or 50 degrees between daytime and nighttime temperatures. And over time, all that expanding, contracting can cause those screws to loosen up just a little bit. And you know, a little bit here, a little bit there, it starts to add up. And next thing you know, 5 years later, all of a sudden what was tight is now loose. So I'm going to get into that more in troubleshooting, system troubleshooting. We'll talk about that in the next webinar. But one of the things to always check is to make certain all your wires and connections are tight. Because again, if you have, these can loosen up over time very easily. They can also loosen up in shipping, by the way. That's another one. Vibrations from shipping can also loosen them up as well. So again, that's something you want to look for when checking these things. Also, the diodes, looking at this, the diodes, these are soldered, so I don't want to worry about so much, but if you have ones that are not, that are installed mechanically with a terminal, with the screw terminal, something like that, they could accidentally be installed backwards, they could be shorted, or they could be filled open. So that's something else you could spot here by going through that. I'm going to go into more detail on what the values are you're looking for that tell you what might be going wrong. Okay, so reverse polarity again. So if you get a negative number when you do your VOC test, that indicates that the wires are reversed. The simple solution is just flip your wires around. So that's a pretty easy fix and a pretty common one we see, especially during installation. So if you're doing an installation, if you're having a problem, that's a pretty common one that we see. Okay, if you've got a open or shorted wire, okay, so if you got an open one, actually you're going to get a zero. You're going to get a zero reading either way. That's what's interesting is that so you get a zero value. You could be getting either. Okay, so what you want to do is you want to trace the wires till you can find where that is. Odds are, and you're just going to want to, wherever you were starting at, just keep backing up and just keep doing your VOC test and keep going back until you find the problem. It could be anything from, again, a problem in the junction box or combiner box or anywhere in between. Again, so just want to kind of trace the wires back to figure out where that is. And then once you do that, fix the wire. I did not show that here. I had again, another one where a wire, another one recently, troubleshooting call, where a wire had output wire had been broken. What had happened was the insulation had gotten gnawed through by a rodent. Then the copper wire was exposed, it corroded, and it broke. So when they went to go do an inspection, actually, when the system had failed, they had seen that the wires were literally disconnected. So again, you could just trace the wires back till you find something like that. Okay, incorrect array wiring. Again, if you're going to find numbers that are a little off, either too high or too low. And again, this goes back to those VOC numbers. So the first two are pretty easy. If you've got a negative number, it's been reversed. If you've got a zero number, there's either a shorted wire or a disconnected wire. But if you've got a number, but it's not what you're expecting, let's say it's a, let's say example for a 12-volt module, typically you get 22 volts as your VOC. If you're only getting 11, that can tell you something, okay? But let's say you have two 12-volt modules wired in series to get a 24-volt output for a 24-volt battery, and you're only getting 22 volts out, then you've probably miswired it in some way. Or let's say you've got the 4 modules, okay, and you're trying to, 4 12-volt modules, and you're trying to wire them 2 in series by 2 in parallel to get you, again, a 24-volt output. You're getting numbers aren't making sense. Look for that. And when you have multiple modules, it's very easy to make a incorrect series parallel connection inside a junction box somewhere. And you're going to find that, again, if your voltage is too high, you've probably wired too many in series. If it's too low, then you've probably paralleled too many, and they should have been series and they're parallel type of thing. So you want to trace it back, look at, take the module junction boxes apart, look at them, and figure out where the wiring went wrong and then fix it. Again, this is a pretty common problem during installation. So one of the things during installation is you always want to check before you start turning stuff on and looking at things. The VOC test is a good way to double check you've wired your way correctly, whether it be for reverse polarity or for series parallel. So again, very simple test that can tell you a lot of information. Okay, and this is a great example of the diodes I was talking about earlier. These can actually be removed and tested. These wires here, again, I had a call where one of these was loose. I forget which one it was, but one of these got loose for whatever reason over thermal cycling. So these are things that you'll want to check inside the junction box if you're having issues. So fill bypass diode. What ends up happening is that actually the way bypass the diodes are installed, it actually splits the module in half. So there's a diode for every 18 cells. Okay, so sometimes I see people miswire a solar module. The other way you can miswire it, say you have a, as I mentioned earlier, you could have a 12-volt module that is has a 22-volt VOC, and I'm only getting 11 volts out. Odds are you probably wired to the center here. You probably wired to this terminal in the middle that's between the two diodes instead of at the other end. And that's a I've seen it happen before sometimes, and that's a common one. So if you're getting half the voltage that you're expecting, you've probably done that. You've probably either miswired it to there, or you've got a bad diode or a diode problem. So I would that's a big indication if you're working on a 12-volt or 24-volt module, and all of a sudden you've got a voltage like that. I go straight to the module junction box. I would look in there to figure out whether there's a wire issue, a wire got disconnected or connected incorrectly to the wrong terminal, or whether you have a bad bypass diode issue. Okay, so and if you can remove it, you can test it with a meter. That's another. A lot of meters have a diode test function on it. You can remove it and do that as well. Make certain you install it correctly. You don't install it backwards when you put it back in. So we talked about bypass diodes early, and this is why. A lot of times, again, if you're seeing a module that has half the voltage output, there's probably something going on there. That could also be caused by shading, by the way, too. So that gets back to checking that shading issue and doing this on a sunny day. If you have a single cell being shaded, you can also find this half a voltage problem as well, because what's happening is that the shade has caused one of these diodes to become active, and that's taken out half of the solar module. So that means the other one's still functioning, which means you're going to get half the voltage as well. So again, if you're seeing a half a voltage, you may have a shading issue as well, but that should be easy to check visually without having to actually open up a junction box. Okay. So just some of the things to look for when you're doing the VOC test, and then some of the ways to correct it and what would cause it. Okay, I already mentioned the incorrect loose wire. I think we've covered that pretty well. Corrosion as well is another one. If you have an older system, that's another one. Look for corrosion on it. That's a problem, especially in high humid or salty environments. Fill module. Also, if you were getting, if you check, getting back to this little diagram here, if you check your plus and minus at these terminals and you've eliminated everything else at the problem, you're still getting 0 volts out, there's a very good chance the module's probably failed. You could do a short circuit current test as well to confirm that. We'll talk about that again in our next webinar. But if you're getting a 0 VOC at the output terminals of the solar module, there's a very good chance that you have a bad module. Typically what happens with these are, if I can get back to my solar module real quickly, what will happen is that the little lines that connect these cells together, the little ribbons inside, they can fail over time. So the connections can go bad or something like that. So what will happen is if you get a 0 voltage out, what's typically happened is that usually one of the little interconnects inside the cells have failed, especially in an older module for thermal cycling. Again, all that expansion and contraction is putting stress on all the little interconnections that connect these things together. And then they can just kind of fail over time, and generally they'll fail open is what typically ends up happening, and you'll get that zero VOC on the output. So that's a common problem on older module. All modules should all be tested from the factory before they're shipped out, so generally you do not find that on a new one. So again, that's generally something you'd find on an older module, typically from thermal cycling, something that might be out in the field for 5 or 10 years or more. Okay, so it's generally an indication for a failed module. Again, I'd probably go on to do an ISC test to confirm all of that. But if that were the case, you'd obviously want to contact the module manufacturer for further testing to determine whether it really is bad or not, and if it is, if it can be replaced in the warranty. Again, so there's a lot of benefits of short circuit current tests as well to double check some things. We'll talk about that more. The important thing to keep in mind with both of these tests are, especially the short circuit current test, is that these are done with live solar modules. Anytime sunlight is present, there is current and there is voltage. So there can be a shock hazard associated with this, and when dealing with the current, an arcing hazard. So generally we try to tell people to do the ISC test on just the module or string level, because you want to keep that current to 10 amps or less. Most multimeters are only rated to 10 amps. You want to keep that current down to that, so that there are no problems with damaging your meter, and also it minimizes the arc too, because the arc when you do that's going to be pretty big. So that's also kind of a safety hazard as well. I'll talk about that more when we talk about the test, but there are additional things that you can find with that test. Okay, we're running low on time here, just got 10 minutes left, so we're just going to briefly run through combiner box and what's required or not. There's some, what I've noticed is that there's some people talking about the difference between grid tie and off grid again. The NEC code that people refer to as why you don't need a combiner box sometimes is article 690.9. And the problem is there's an exception that people kind of miss that says that the exception says that the overcurrent protection is not required except where one of the following applies. You'll notice number A says external sources, including batteries. In an off-grid system, you've always got batteries, so you always need to have overcurrent protection on the solar array or on the solar modules. Now, if it's just a single solar module, the battery can suffice for that one. So if you have a fuse or circuit breaker battery, that will suffice. However, as we pointed out earlier, having one for the solar array is really handy for troubleshooting and doing the VOC test. Okay, now if you've got more than one string or module in parallel, do you need to have an additional circuit breaker or fuse or not? And this kind of gets back to that diagram at the very beginning with the terminology. It was showing one on each string, and in most cases you're going to need to have one. And basically what NEC also says is that if you take the combined short circuit current times 1.56, if that exceeds the maximum fuse rating for that module, and again, all modules have what they call a series fuse rating or a maximum fuse rating for it, that check your spec sheet. Anytime you look at a module spec sheet, there's a line on there that a lot of people ignore that talks about the maximum fuse rating. That's the maximum fuse rating for that module. And getting back to those little interconnects, basically what that means is that that module is rated for maximum current, otherwise those interconnects will fail. So you end up using those as your fuse, which is not a good idea. You can have a hot spot possible, and that hot spot could get enough to cause flames, which is an issue. So for safety reasons, you want to make certain you adhere to that maximum fuse rating that is on the module spec sheet. Okay, so I'm just going to do a quick example here. If you've got, say, a 190 watt module with an ISC of around 5.8 amps, but you have a max fuse rating of 10 amps, you're going to have a circuit breaker or a fuse for each string, because if you put the two together, you're 11.6 amps, okay, which is much higher than the 10 amps you're supposed to have. Now, if that fuse rating was 20 amps, then that's not a problem, because the combined current times 1.56 is only 18 amps. So you could get away with one fuse or circuit breaker for those. But that's if the fuse rating, if the maximum fuse rating was 20 amps and not 10. So again, check your module spec sheet and see. But in most cases, 90% of the time, you're going to have a separate fuse or circuit breaker for each string. Okay, now, let's see. Now, just because, now what this tells you is you're going to need some type of overcurrent protection. Where that is up to you. If you've only got one or two outputs, you may want to go ahead and combine that with your charge controller. But if you have more, well, you maybe have like, I don't know, 4 or 5 or 6 that all are in parallel, you might just want to put in a combiner box at the solar array and then just have one output cable going over your charge controller. So whether you go with one output and a combiner box at the array, or multiple outputs and do your combining at your controller, that's up to you. It just depends on what works out better, whether you want a couple outputs or many, or where it's easiest to do that combining. Okay, we got just a few minutes left for some questions. Again, as always, we have a whole bunch of great tech notes on our website. I mentioned that we've got a tech note on how to do the VOC and IC test. That's a new one. We're putting out a new one right now on the bypass diodes if you're looking for more information on that. And again, this webinar and all the other ones are recorded and they're up on our website within 24 hours of the webinar itself. And again, just a whole bunch of great resources, information there if you want more details, or if you want to try to go look at something in more depth, because I know we're covering everything very quickly because there's a lot of material to cover in a short amount of time. So that all being said, again, just another plug for our upcoming webinar on the basic system troubleshooting. And the one after that we have scheduled for September 20th, and that's solar battery fundamentals, and that's going to be a joint webinar with MK Battery Deca. Okay, so I think we have just a few minutes for some questions. Errol?
All right. So we got a couple questions here that we've had throughout the presentation that I want to cover here really quick. So one of the things that I wanted to address is whether or not what the efforts are from module manufacturers to try and address or negate shading, and is there anything that is actually effective in combating shading, or is it simply a physical limitation to the way that the modules are set up? Specifically, would increasing the voltage per cell help to eliminate this?
Very good question, actually, very good question. Let me try to address it in a couple ways. There's nothing you can do to help the cell, because as I showed, if the sunlight on that cell is 0, the entire module goes to 0, or at least that portion of it, because there's a bypass diode that's going to bypass it. What that then means is if you go to some of our other tech notes with regards to voltage drop issues and temperature correction for voltage drop, basically what ends up happening is that the voltage gets reduced such that no current will flow to the battery. Okay, now what you can do is the only way to really work around that, and this is where maximum power point trackers come into play. This is what they do basically in residential, is that bypass diode will bypass that section of cells or the whole module, whatever it is, and then everything else in series can still be used. But that means you've had to have wired enough cells and or modules in series to have enough voltage left over to charge that battery. Okay, now that still means you're going to lose that amount of power, but you might have enough voltage. But again, in order to do that, you must have a maximum power point tracker, and you must have wired it with an additional voltage. So let's say, let's say you might have a 12 volt battery, and you've put two 12 volt modules in series to an MPPT. Then if one of them goes out, the other one will still work. Okay, type of thing. Obviously, they're in parallel. It does not have an effect either. Okay, it's only the series connections that are an issue. And again, the only way to really, you can't really address it on a module level. It's not possible. The only real way to address it is with a maximum power point tracker. But again, if you don't have enough voltage for when that string or that those section of cells is eliminated, then it's not going to help you anyway.
All right, thanks, Rob. That helps. Another real quick question. For the short circuit current test, rather than using an inline multimeter, a simple DC clamp-on meter would work as well, correct?
There are two problems with that. I mean, yes, it would work, yes and no. The thing is, you're still going to have to find a way to short circuit it anyway. I find it easiest just to short circuit through the meter. The other problem is the clamps-ons aren't as accurate. And depending
Okay.
upon the module you're working with, if you're working with a big module, that's probably fine. If you're working with a small
Okay.
module, it's going to give you an inaccurate answer. Some of those are only accurate to within an amp or something like that. If you're working on a
Okay.
module that only has a 2 amp output, that's going to make your readings a little false. Plus, you still need to do that short circuit connection somewhere anyway.
Okay. All right. Thanks. I do have one more question on whether or not it's possible to make repairs on those intra-cell connections within the module that you mentioned can fail sometimes over time. Is it possible to remove the glass layer to make those repairs, or does that area need to remain sealed? I actually don't know myself.
Actually, I do because I did work for module manufacturer at one point that I will not mention. But no, the laminate, the way there's a laminated with the EVA, which is basically a glue in there, it's a clear glue, you cannot remove the glass. That is not possible. Now, that being said, you can get to some of the ones on the back. So if the connection failure is on the front, no, you can't get to it. But if there's a connection on the back, yes, you can. And it has been done by some manufacturers before. They can remove the backskin Tedlar, they can repair that connection and then reseal it with some type of new Tedlar backskin or silicone or something like that.
Okay, thanks. I do have one more final question on explaining one more time the function of the bypass diode within the solar module.
Okay, again, what the bypass diode does is when that cell or a few cells are shaded, those cells are going to want to take current. Remember, it's kind of like an LED in reverse. So when they get shaded or when the sun goes away, those cells are going to want to take current. So from the other cells that still have sunlight on them, they're still producing current. Now you have these shaded cells are going to want to take current. So the current from the sunlight is going to go into the shaded ones. To prevent that from happening, those bypass diodes end up activating. Okay, so the voltage over them, the forward bias voltage over them shifts, and it causes them to basically activate, and it causes the current to go around that section. Again, we have a tech note we're putting up on our website right now to address this, because as I was putting this webinar together, I realized that was not addressed very well. So I've created a tech note just for that. And again, what will end up happening is it'll bypass that section, and by doing that, it'll avoid the hot spot. And again, if you do have a max power point tracker, it will allow the rest of that solar module or string to function. And again, it literally just bypasses it. It just takes that section out. Generally, you're going to find that a bypass diode is installed every 18 to 24 cells. And by the way, that is required by, I think it's UL. That is required by code. That's why they're in there. So it's required by the module manufacturers to have it in there because of that. Because without that, you get that shading, you can create that hotspot, and that can become a hazard.
Okay, I did have one last question while we have the time. Whether or not there's any maintenance considerations to module backings or Tedlar backing or anything that needs to be considered about the material on that back end of the module.
Good question. Generally, no. There should not be. Now, if something has, for some reason, it has gotten damaged, it may have gotten scraped. Another a common one is you know, as people are assembling these things, they may hit it with a screwdriver or a wrench or who knows what, and they may have scraped it. Then it needs to get sealed, because if it's not sealed, it will allow the environment to get in, and it could corrode those connections we mentioned earlier, those interconnects. So if that happens, we usually recommend that it be sealed with a high-grade silicone. Just like silicone caulk is all you need. I mean, silicone caulk is readily available at any hardware store. So that would be the only maintenance I would see again, and you want to catch that before it's been compromised basically, because once that's compromised and the corrosion gets in there, then the module is going to fail, and there's really not much you can do other than replace it. But again, there should not be any maintenance unless you notice there's some type of scratch or scrape or something that has damaged that back skin, that Tedlar, and then again seal whatever that scratch is or gash or whatever it is with a high grade silicone.
All right, thanks, Rob. Well, I don't have any more current questions, so we'll give people another moment, and unless there's anything else, then I think we're good.
Okay. Thank you, everybody. Again, we'll cover some of this information again in our upcoming webinar on the 23rd with regards to system troubleshooting. So we'll go over that again. And again, this will be available up on our website within 24 hours if you want to go over it again. And check out our tech notes because a lot of the information I covered is included in our tech notes in a little more detail, where you can read through the language and look at the diagrams a little bit longer, so that might help to answer some of these questions with regards to the shading. So we have a tech note on shading, another tech note on the tests, the VOC and the IC tests, and again, we have one that should be up there in the next day or two with regards to the bypass diodes and how they work and why they're needed. Okay, if there are no other questions, then thank you, everybody, and I look forward to seeing you on our next webinar. Have a good day.
Thanks, everybody. Appreciate it.